This one we're going to talk about some of the uses of radiation. So why on earth would we want to use radiation on a person? Well, as we talked about, for the most part, getting hit by radiation on its own doesn't do anything. That is, you're always bombarded by radiation. There is radiation coming from the sun. There's radioactive elements in the ground that slowly decay. If you eat a banana, it concentrates potassium. It's a good source of potassium. But potassium-40 is a common radioactive element in the earth. And so if you eat a banana, you technically get a slightly higher dose of radiation for the day than if you hadn't eaten that banana. And so we just get radiation from all sorts of sources. And we take a little bit of damage, and then we repair it, and that's it. We just keep going. When you are a human, you are about 1 trillion human cells, and you replace tens of millions at minimum a day. And so, losing a couple extra 10,000 is nothing on top of that. It's a scraped knee. Your body is just built to replace it. Where this becomes useful, though, is when we need to remove certain cells. And so radiation is a way to cause cells to terminate without having to cut them out. And this is important for various treatments. So one common one, don't think about any more. Here's my person. Well, in your neck is your thyroid. Thyroid does several different things. One of the important parts is that it uses some iodine in order to create a few molecules that our body needs. So we don't need a lot, but we need a tiny amount of I2. Well, of I minus, really, but iodide. Our body can process it and change it around. So what happens is, as you grow, your thyroid has to grow with you, and that signal tends to come from your body saying, hey, I don't have enough of this molecule, thyroid. Grow bigger so you can make more. Problem is, if you have no iodine or iodide, then you can't make more. The thyroid tries to get larger, it doesn't produce any more chemical, so the body goes, hey, I still don't have enough chemical. Hey, thyroid, get bigger. Still, if you don't have iodine, that didn't help, and so your body sends a signal again, thyroid, get bigger, get bigger, get bigger. What ends up happening is your thyroid swells. In the old days, this was goiter. Goiter would be when the thyroid swell up really badly. It could swell so bad that it ends up pressing on the throat and on the nerves and on the veins, and could be very problematic, if not lethal in some rare cases. So, well, in the modern world, most places goiter is not really a problem anymore because we iodinize salt. That was how we fixed it. If you ever wondered why iodinized salt exists, we put a tiny little bit of iodine in every packet of salt. Just a milligram or 2 per serving or less. But that's all you need. And so, because that gets cooked into everything, everywhere, everyone always has the iodine they need. And so, unless you've got a few parts of the world where they just can't ship that in, and there still are some places this happens, for the most part, goiter as a result of lack of iodide is no more. But you can still have thyroid expansion, and hyperthyroidism is the growing of the thyroid. And so this is really about hyperthyroidism, but the old disease, say goiter, was more or less the same thing. So what happens is, well, iodine 131 is radioactive. I believe it's beta decay, but I forget off the top of my head. But it's radioactive. Not particularly badly, but it is a little bit. And so what will happen is we will give a patient with hyperthyroidism a dilute solution of iodine 131. Enough that's spread out over the whole body, it wouldn't do a lot of damage. But the thyroid naturally grabs all the iodine, it stores it. And so, I'm about 100-ish liters. So if you have 1 mole, and it wouldn't be anywhere near that much, over 100 liters, you have 0.01 molar. But if you concentrate that down to 100 milliliters, 1 mole over 0.1 liters is going to give you 10 molar. We increase the concentration, which means as far as your thyroid cells are concerned, there is way more radioactive iodine around. Realistically, we're never giving you a mole, but just to highlight concentrations here. The net result is, as it concentrates in the thyroid, it becomes dangerous level to the nearby cells. But that's exactly what we want. Because if you've got a bunch of cells, and you cut part of them out, so you come in and you just hack those out, the remaining cells will scar over. They don't connect with each other, so they'll develop a scar. Your thyroid's also near veins and nerves and things. This is a bad option. This is not something that we actually want to do. And so instead, what will happen is if you can kill just one cell here, other cells will slide in. If you can remove kind of one cell at a time, the body's pretty good about moving things in. So bit by bit, as these cells die one at a time, your thyroid will shrink. So this is a way to shrink your thyroid without leaving the scar tissue, without risking the damage. And so by using just a little bit of radioactive material, we can cause it to shrink a little. We give you another dose, a month or whatever later, it shrinks a little more, another dose shrinks a little more, until we're down to the size that's reasonable, and we just stop giving you the radioactive iodine. And so this is a way to target, or selectively target and remove cells that need to be reduced in order to achieve proper function. So this is one use of ingesting a radioactive material. Now a lot of times we're not ingesting them. We might implant it, so little metal pins are implanted in the prostate so that they can destroy local prostate cells slowly if you have an enlarged prostate. So that's one way you can shrink down a prostate. Same kind of idea, it's just instead of ingesting it, the thyroid we were lucky, it pulls in iodine, but prostate doesn't do that, so we have to put little pins in it. But other things like, let's think about if you've got a tumor of some kind. So in this case, you've got a brain tumor. Now sometimes we can try surgery, but every once in a while you run into a tumor that you can't safely cut into. There's no way to get to it. And so in the old days we would try chemotherapy. Chemotherapy is the use of a chemical, various types, whose main goal is they cause cell death for cells that are trying to divide. And so when your cell tries to divide, it has to duplicate its DNA and pull it apart to the two new cell halves. If you can disrupt that step, the cell will terminate instead. It fails and it can't keep going. Well, cancer cells do this all the time. They're constantly growing, where other cells in your body take a lot longer. So chemotherapy, the idea is give a drug that targets fast-growing cells that will hit the cancer more than anything else. And so the idea is it does more damage to the cancer than it does to the rest of you. But there's kind of a limit. It is doing damage to the rest of you. And so this is why people in chemotherapy tend to be fairly ill. White blood cells also divide very quickly, so you lose a lot of white blood cells. Hair cells grow very quickly, so you tend to lose your hair. And it just does a little bit of damage everywhere, but more to the tumor. And if the tumor was small enough and manageable enough, you can destroy the tumor before critical systems in the body. Well, modern treatments try to mix chemo and radiation if we can, because radiation can be used, especially when it's an inaccessible tumor. What will happen is, and this is one of my favorite modern techniques, gamma knife. We'll use a cobalt-60 source or the like, some kind of gamma radiation source. And we'll have a little box, a little aiming spigot, and we'll let just a little gamma radiation out. Well, that gamma radiation passes through, And it is low enough that it doesn't severely damage any of the cells. We make sure that you have just a little gamma. It penetrates through, doing a little damage to everything in its path. But not enough to really hurt the cell. But then we move the box and we do it again. And we do it again, 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 and we do it again. Over and over and over and over from all these different angles. Well, any one path, nothing along it really got enough damage to be worried. But the thing at the center of all the paths, that takes repeated damage. That gets damaged many, many, many times, and those cells break apart. They cannot operate. They take too much damage to keep functioning. This is now accurate enough that we can get down to cubic millimeter volumes. And so with a good scan, we can literally plot out where the cancer is and then basically terminate all the cells within that volume. And that result is a massive reduction to the tumor, which then when you give chemo, there's not nearly as many tumor cells that need to be targeted, and so you don't need the chemo for as long. And so this is one of my, I think, more interested for external radiative treatments. There's some radiation you ingest and use inside, there's some that are from the outside. Gamma knife, proton therapy, all sorts of other stuff. But this is an example where we can utilize radiation, the most damaging type gamma, in a very precise fashion to achieve a beneficial outcome. Well, on top of tumor treatments, big use is imaging. Now, we talked a little bit about X-rays. We want to see inside the body. X-rays are great for that. They see your bones. If you do a certain set of CAT scans right, you can see organs inside the body. You can even make a 3D image of them. Technology's been pretty great with where it's going with that. But one of the things for using radioactive materials, nuclear radioactive materials, is that it also helps us see the vascular system. And so certain types of barium dyes will kind of flow through your vascular system, and then they give off a little bit of radiation, and we can have a sensor that picks them up, and it can map your veins and arteries, map the vascular system. If we see a spot where you should have blood, and there's very little signal from the dye, that tells us something's wrong. There's a clot or a damage. For some reason, you're not getting blood flow to that area. So it's very useful for looking for strokes and lack of flow for heart attacks and things like that. Additionally, there is a PET scan. Positron, Emission, Tomography. So this is one of my favorites. So positrons are a little bit different. They are beta plus. So beta was an electron. Beta plus is a positive electron. Now if you remember, electrons had to be negative. That was what made them electrons. That's because this is an antimatter electron. A beta particle is just the antimatter version of an electron, and certain decays produce them. If you've got a carbon 11, proton 6, neutrons 5, this breaks into boron 11 and a beta particle. Sorry, a positron. Beta plus. So this becomes a 5 protons and a 6 neutron. Well, that means a proton went away. A proton turned into a neutron. I had a proton, it became a neutron, but you cannot destroy charge in the universe. It must always be equal. So my positive can't just go away, so it has to kick that charge off on something, and it does it as an antimatter electron. Well, why is this useful? Well, antimatter and regular matter, if they ever meet, completely annihilate each other into a massive amount of pure energy. So if that beta particle ever touches an electron, which, okay, you are full of them, every atom has many of them, except hydrogen. They have at least one, though. Right? So if this ever bumps into anything else inside you, it blows up into a bunch of gamma radiation. This is mass completely converted to energy. There's nothing left but pure energy at the end. So this is powerful. There's a reason Star Trek and sci-fi has antimatter reactors powering everything. They are enormously powerful if we could ever harness them. Unfortunately, well, we can only make little bits. Where is this useful, though? Well, if we give you glucose, a sugar, it's a ring system with a bunch of OHs. Vaguely looks like that. And there's carbon, 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 carbon. Add a bunch of hydrogens. This is glucose. This is the sugar we think of when we think of energy. Well, two types of cell and parts of your body really love glucose more than the rest. I mean, all your cells do, but your brain and tumors love glucose. Tumors need energy. They're trying to grow constantly, so they have to pull in as much sugar as they can. Way more than normal parts of your body. Your brain is also primarily run by sugar. We don't really burn fats in our brain, it's mostly glucose. So, you have a person. Here's my wonderful art of a person. There we go. And you give them this, and then you put a scanner on them, and you watch, and what'll happen is you'll get little radioactive events kind of all over. The sensor will pick up a few of them. Well, if you have a tumor, say a lung tumor though, because there's so much more of the sugar in there, you'll just get more of those events, and also in your brain, because your brain has more of the sugar. Anywhere where there's a higher concentration of the carbon-11, you'll see more signals. Now, we don't have to give you very much. This is an incredibly tiny amount of carbon-11. Like, smaller in molarity than we've ever worked with. Because you don't need a lot to detect. Individual gamma rays can be detected. So normally in chemistry, we're talking about moles of things before we notice. You can pick up one gamma ray. So we need so little of this spread out through the body that the damage it is doing is negligible. Again, it's just so little compared to the size of us that we don't care. But the device can pick up where it's coming from and say, hey, sure, you got the normal spread around the body and the concentration of brain, but there's this extra bit in your lungs. This is a problem. The only thing that would be there would be a lung tumor. So we need to do some more experiments and possibly biopsies and things. The other consequence is, if you ever have a PET scan, you get to tell people you're going to create antimatter explosions in their brain, which is one of my favorite things as a sci-fi and scientist buff. Antimatter explosions in your brain, and it's for your benefit. Because again, realistically, you're talking about a countable number of these events actually happening. And your brain is, tens of billions of cells. So a small number, tens, hundreds, thousands of events, even if each one could actually destroy a cell, it's not doing a significant amount of damage to your brain in any way. And as a result, we are able to image quite nicely with this to find tumors. So that's a couple different uses for radiation, radioactive materials. We can, in certain cases, ingest or implant it in the body in order to selectively reduce the size of certain organs, thyroids, prostates, and like. We can selectively target and damage volumes inside the body in order to destroy malignant cells or cancerous cells. We can also see inside the body. Barium dyes for vascular, the PET scans that track where parts of your body that want extra glucose are, which tumors and brain. X-rays so we can see your bones. Like, people don't anymore realize how strange that was, but it's only a little over a century we've had it. And when it first came out, Like, the phrase when you get an x-ray was, "I've seen my death." You never saw bones unless someone was dead or dying. You couldn't get into the body. There was no way to do that. There was actually a bit of superstition attached to it early on, but they realized how unbelievably valuable it was as a tool, and so they kept developing it, which unfortunately, because they didn't realize it was dangerous if you overuse, kind of the people who first discovered it died from standing in front of it all day. Like, one of the first guys to do it had a screen that he could put his hand on, or under, and it would shine up to a phosphor screen, and he could draw his hand bones. And then he'd move his hand, and he could see how they flexed and rotated, because no one had ever seen a functioning interaction of bones. That was impossible. And so there was so much to learn, but he discovered later, by continuously exposing himself to high energy x-rays nonstop, that it was problematic. He developed cancer in the hand, they had to amputate more and more of his arm, and it eventually claimed his life. And one of the last, I forget the exact quote, paraphrasing it, was that he hated to see that his wonderful discovery may have a dark side, but it had too much good to do, and he encouraged everyone to keep working to solve how to make it beneficial. And so, again, it comes down to the amount and the types. We are always bombarded by radiation. This is around us all the time. The amount is what matters. Different types be a little more dangerous than others. So maybe you can take 1,000 alpha, 400 beta, 100 gamma. Like, you might need less of certain amounts for the same amount of damage, but you can take some damage. So yes, if you ever have a patient who is concerned, it does do small amounts of damage the same way scuffing a toe or stubbing a toe or scuffing a knee does. But you are built to heal from that. It is only if you have incredibly high amounts that you cannot heal in time from that we really have problems with radiation. Alright, and that'll conclude this video. We'll pick up in the next one with a comparison of amounts and where on Earth, well, not on Earth, do we actually obtain radioactive material from?